So I work for Shearwater Geoservices. I have some background in physics, actually, and I've been working in high-performance computing, a lot of RTM, actually, for 10-ish years. That said, sometimes I think my best qualification was actually growing up in a bakery and doing dishes and trying to get them done as fast as possible. So I'd like to make some analogies, at least, throughout the talk to that sort of situation. So we'll see how it goes. So today I'd like to talk to you about the techniques that we use to optimize SRME on highly parallel hardware. So that means both GPUs, but also CPUs as the core counts get higher and higher. Currently, we had an implementation, which is probably pretty similar to the industry standard. It does kind of the normal OpenMP for loop serial section, OpenMP for loop serial section. And as that core count increases, and especially if you start to migrate a code like that onto GPU, then you crunch down those for loops, but you still are stuck with your serial sections. So we need to find some other levels of parallelism, some other way of actually filling in those gaps, but try not to run out of memory and try to read in our data efficiently. So the problem is embarrassingly parallel. There's a lot of avenues that we have in order to do this. But if we don't explore any of the redundancy in how we read in data, we're just going to be stuck with a disk-bound problem. Also, we'll look at a little bit of the background, the geophysics background, and see why dynamic scheduling is so important. And that's because the output cost for all the different points that you're trying to compute is significantly different depending on things like offset. So going back to the very, very basics, what is surface-related multiple extraction elimination in the first place? So many of our imaging algorithms, when we're trying to make a picture of the underground, assume that we have no multiples in our data. But when we actually collect it, that's not true. So we have to find some way of estimating those, and then subsequently we can subtract them. How do we do that? Well, actually, we've acquired a whole bunch of data, and we can look through that data set, and we can find portions of the data set that actually represent the multiples that we're looking for. So what do I mean by that? If we look at strictly the enlarged source-receiver pair that you see here, if we were to try to estimate some of the multiples that come into that collection, then we can put a bounce point somewhere on the surface, and we can see if we can find a recording to that point. And then we have a source-side recording to that point. And actually, if we look elsewhere in the data set at some different shot, then once upon a time, our shot was at that location. Therefore, we can pull that piece of data, and now we have both legs. We can convolve them together, and we can get an estimate for the multiples that are in there. Now, we don't always have a perfect synthetic, so the multiples and the bounce points that you're looking for might actually be offset from the true data that you have. Therefore, we need to apply some sort of correction, and then we can stack over all the different possible locations that we have these bounce points, and that gives us our final estimate. What does that mean from a high-performance computing point of view? Well, that means we have to load in the entire data set, all the headers at least, so that we can start searching around and find the traces that we're looking for. Then for every single source-receiver pair we have, say, tens of millions of traces in most of these examples. We're going to go through each one, and then we'll generate a set of bounce points. That's typically on the order of 1,000, 10,000 bounce points that we'll look for. And for each one, we're going to try find an appropriate source, find an appropriate receiver, read them in from disk, presumably, or some other source of memory, and then apply the corrections, convolve, stack, output. So that can be divided up into several different parts that stress different parts of the hardware. And ideally, these days, we need to make sure all those hardware parts are moving simultaneously. If I go back to the bakery type analogy where I'm doing dishes, well, in this case, I'd talk more about if we're trying to sell a loaf of bread. So if you go into a bakery and you try to buy a loaf of bread, and someone tells you that it's not actually even baked yet, well, you're going to leave. You're not going to come back. So typical speeds for compute is we're looking at 10 terabytes a second of read speeds once our memory is local, and it's a memory-bound problem. Whereas if we go back to disk, we're looking at maybe 10 gigabytes a second, if you're lucky, maybe on the order of megabytes per second for scattered reads from a network disk. So that's 10,000 times as much time. So we're going to have to get way, way, way ahead and actually read in that data in advance. And probably the least favorite job I have at a bakery is how in the world do you guess at the beginning of the day how much bread you actually need to bake before the customers show up. And it turns out for SRME, it's compute intensive to determine what data you actually need. And if you just kind of guess in advance, then you're going to have a huge memory footprint, and it doesn't work. And you're kind of stuck with a compromise between figuring out what you need to load and actually loading it, or being excessive in what you load. Going back to some more technical theory, I don't really want to spend too much time on this slide, but what I do want to highlight is that somebody else figured out all the algorithm for this. It's well-defined. There's literature for it. And it's known kind of what density of bounce points you want, how big your aperture needs to be. And it actually works in a much more general situation than the previous slides that just show kind of a constant water with a flat horizon. Going to an actual data set, to be honest, it's a relatively small data set, Pluto data set available from Geoscience Australia. We can start plotting these bounce points and looking at what are we actually computing, how much memory do we need to use. And the primary architecture that I worked on was a 4X H100 machine with 96 gigs per GPU. It had a terabyte of CPU RAM and local SSDs. So I can cache data in various places. The actual bounce point footprint here, I apologize, it's a little difficult to see, but each one of those pixels surrounding the source receiver pair is one of the bounce points that we're going to have to go over. If we start to look at further offsets, the middle plot is the one that I rendered on the last slide. So it looks like a tiny puddle compared to at the far offsets where we have many, many bounce points to consider. If we start to look at the very top, where we combine all of the an entire shot gather and all the bounce points, then there's quite a few bounce points that are there, but you also see that there's a lot of redundancy between all of those receivers along a cable. So the way the algorithm works is you end up having a source side leg, if you recall, and the receiver side leg. So within a single shot, we can pre-compute all of the source side information, and I think that's pretty normal in industry standard. But you're going to run out of memory. This is a relatively small data set, and especially if you start to move to OBN data, there's no way you're going to fit all those bounce points for all the shots. So we have to find some way of cutting that up and working with that. So what does the existing code look like? Again, it's not really documented in the literature to our knowledge, but I do believe that most industry implementations are similar to this. So you read in all your data, you pre-compute optionally some of the data that you're going to need, and then you go back, put it in, say, a local SSD instead of having it sit on some network file system, and start iterating per source, do some pre-compute, and then iterate over all the receiver locations. Each one of those sections is multi-threaded over bounce points, but that's really the only spot that it's multi-threaded. So what do we want to do? Well, we want to keep all parts of the hardware busy. So if you look at the previous slide, then especially the first part, if we're caching data from the network file system, then that initial parsing is a whole bunch of CPU prep work. Then we have a whole bunch of disk read, and then we finally get to the actual compute. So that's something that we can overlap together. We also want to implement this on GPU, as I talked about, but ideally we don't want to rewrite the code multiple times. So let's see if we can reuse a lot of the infrastructure for both CPU and GPU. Now, no matter what you do, there is going to be some slowest component. And if I go back to the bakery, then for me in high school, that was the dishwasher itself. So we'd get out, we'd finish school, we have to clean all the dishes, clean all the floors before we get home. And the dishwasher itself is your limiting factor. So you got to get those dishes in, close, and then you can go clean all the floors, come back, etc. So we want to do the same thing. But no matter what, there is going to be some slowest component, but everything else should happen asynchronously. And if you look at benchmarks and stuff, then they'll be actually cost-free until they become the bottleneck themselves. Throughout this project, we moved in different stages. So there was an existing implementation on CPU with a whole bunch of different features. There's also tapers, etc. So you want to take all that code, port it onto GPU, get the same result, and not really change it for any customers. So step one, we did that verbatim. Single-threaded code on GPU is slow, but at least we could get the right answer and confidently go from there. Then with the help of NVIDIA, we did some GPU kernel optimizations, and that went great. And at that point, I sort of paused the geophysics side of things, making sure that all works. And we changed one of the stacking algorithms to actually be a deterministic stacking. So if you do just an OpenMP parallel 4 and have some sort of stacking to an atomic add, then that's non-deterministic. So every time you run the job, you're going to get different answers. From a testing point of view, that's pretty annoying. So actually, in the other room, Karthik just talked about some ways of detecting errors for that. But in this case, we made it so that it's completely deterministic. I just do MD5 sums in order to make sure that everything's working as I expect. Then we started to do all the multitasking. And at first, to be honest, most of this is textbook. You make things run asynchronously, et cetera. But I found that there were a lot of idiosyncrasies with the geophysics and the kind of variability of the data sets that made things a little bit trickier. So that ended up being kind of all the work that I've done earlier this year up until yesterday. Going into the future, I would like to look at more systems and start to look at what the bottlenecks are on those systems, especially when you're reading from different types of disks, et cetera. So please, if you're a vendor, love to run something. All right. So going back, this is actually a slide you've seen before for the most part. This is the same algorithm that we had originally. We go to the point where we just port it straight to GPU. Then we get something that looks like this profile at the bottom. And I'm not sure how familiar everyone is with NSYS, but the different colors represent different parts of the hardware that are working. And if we're simply uploading data, running some bounce points, offloading, et cetera, you don't get a very efficient use of the system. So we can parallelize on a higher parts of the algorithm. We got millions of output traces, but we're limited on memory, even at 96 gigs on an H100. So at the highest level, before we had some loop where we would figure out in advance what we actually need to load and read it into some local scratch. Now we're going to read in only the amount of data that fits on a single GPU. So if you look at this in many algorithms that I've worked on, like KDM, RTM, it's a pretty easy thing to figure out what data you actually need. But for SRME, the reads are so variable and the number of bounce points is so high that if you were to do the theoretical version of it, then looking at a couple different bounce points, I think even for the shot that I output for that one plot, I need 220 gigs of data to keep all that stuff if there was no redundancy in the data set. But many of the points are the same, and you can start to collapse it. So you can't really anticipate that redundancy. It depends on some of the offsets and stuff that are in your data, and especially when you have feathering and things like that, the redundancy is going to vary. So we have to just look ahead, just kind of guess, do all the lookups, see how much memory we're using, and then finally pause when we run out of memory, read in that stuff, and then all the kind of core compute happens at a lower level, and itself is kind of double buffered. But at least we can start working ahead, and we can do all the lookups, and then we can start the process again. And after we've done our first read, then everything can be pipelined, and we can have some CPU threads looking, what data do we need, read some in, and then internally we have yet another set of threads that can compute that chunk of work. So I thought that was a great idea, and it worked fairly well, especially on my local machine with the test data set I was given. And then I took it up to some V100 nodes on a real data set. And actually, when I launched the job, it worked fairly well. And I came back and checked an hour or two later, and it was just completely disk bottlenecked. And that actually ends up being related to the fact that there's variability in the things like the water bottom, and that dictates how many bounce points there are. And so at the deeper locations, et cetera, then all of a sudden I hit disk bound. So interestingly, a lot of this came back to caching of the data set. And you need that redundancy, but in order to do that, you need a big enough cache. So it's similar for LRU caches, but in this case, I really had to anticipate the data. So if we end up having a pretty small cache, because we're limited on memory, then it's nonlinear, and all of a sudden we just hit some floor where you're essentially just reading one part, reading again, and bouncing back and forth. And so the actual measurements for that are here, and just the total disk footprint that you read goes through the roof. In fact, yeah, those last jobs I didn't even let finish. But if you reorder your data so that you're working instead of an entire shot at a time, you say, work at only the nearby offsets. Then you can look at the nearby sources, and there's some redundancy in between individual source locations, and that really cuts down your disk footprint. Now, these plots I'm not sure that anyone will understand, but we'll make an attempt. What we're looking at here is the redundancy that we measure for an entire sale line for the two different cases. So if we look at that 9 gig case, and then we can see that there's a significantly different footprint depending on how we sorted the data set. So interactively, I can work through these, and I can see the order at which they were all output. But all of the outputs sum together, so there's all the source locations, all the receivers, all overlaid with each other. And then the redundancy is the color bar. So if I have a single chunk of traces, how many did I load and how many can I output? So say I get 1 million in and 1,000 out, that's a pretty bad ratio. But sometimes I can load 1 million in and I can get 1 million out. So I would call that a redundancy ratio of about 1. So well, especially on CPU, I have enough memory for this data set, especially for a single sale line, and I can cache in all of the data, and the measured redundancy ratio is 1.7. Whereas as I start to get down to a 9 gigabyte cache, then we're rereading approximately 500 traces for every single bin. And it gets worse as your cache gets smaller. So as I said, this is a pretty small data set. So I imagine these numbers will scale up. And so as you work with larger data and OBN, then even the 96 gigs you have on an H100 start to become more and more relevant. And you have to be careful with how that data set is traversed. So that ended up affecting how we do that innermost loop as well. So we have groups of 1,000 traces now to try to keep the memory footprint of how much is pre-computed with the source. And we do all the lookups in advance. Currently, that's done on the CPU, although as I'll show in a few seconds, that lookup is actually currently the bottleneck. So next steps are port that to GPU. Then we can do a bunch of source corrections. And then we group together receivers, but only potentially, because at the far offsets, we end up having a large number of bounce points. And if we group them all together, then our memory footprint is huge. But at the small offsets, then we can batch a whole bunch together and reduce the total number of kernels, and that helps keep the streaming multiprocessors a little bit more busy. And then we output in the end. Now, throughout this talk, I've been saying GPU, as if that was the only processor that we're using. But this task framework also works for CPU as well. So the analogy from a software point of view is that I take a NUMA node and have some NUMA awareness built in and put that as the equivalent of a GPU. And then when it comes to CUDA kernels, what we do is we launch a CUDA kernel, we let it run in the background on our coprocessor, we do some other pre-compute, et cetera, and then we finally synchronize it. So on the CPU, what we do is we have a task, and we have a pool of threads that are sitting there trying to compute the tasks that have been scheduled. So you launch that task, some other thread will pick up the work, and then eventually we synchronize it when we actually have to. So in that case, the streaming multiprocessor and a single CPU core end up being kind of analogous in how you design your algorithm. So those are what I multi-thread the bounce points over. And then beneath that, it's two different codes. So one is a CUDA kernel that's optimized for an NVIDIA GPU at this point, and then a CPU kernel that can be vectorized, et cetera. So overall, on the CPU side of things, that allowed us to fill in all those serial sections. And the 64 core count machine is not actually that high. That's what this was running on. But we still got 1.5 to 2x speed up or so by having some of these things run asynchronously. Having multiple things running simultaneously so that we could fill in those gaps. Measured performance in a more concrete way is for the small jobs, or the original code was taking around half an hour. And then the new CPU code, 19 minutes. So that's the 1.7x. And the GPU code is just under 3 minutes. Actually, a minute of that is still set up because it takes a while to prime your pipeline and everything. And then for the larger jobs, well, it's hard to run, especially a single node comparison. We do have MPI as well, but that has some of its own logistics. But there's somewhere around a 10, 12x speed up, depending on how you count it. To be honest, I wish it was a little better. So these are the actual profiling results on the GPU. And as I said, the current measurement is that the bottleneck is the searches and finding in the data set which traces you actually have to load. So this is probably a lot to take in again, but I do encourage you, if you have any questions or want to see these more interactively, I can show you what's going on. So probably the biggest downside actually to the task-based framework is I now have a pool of threads that are just sitting there looking for work. And then you schedule the work, and some random thread is going to pick it up. So at least for me, I can see with some labeling and stuff what those tasks are actually doing. But it's a relatively random looking plot otherwise. But those ones there are holding up my compute, and therefore on the GPU side of things, there are some holes at this level. And then if I zoom in closer, again, it's not exactly what I want, although I think I figured this one out, but you run out of time to keep optimizing. What we can see is actually, interestingly, I have a couple streams going here, and then there's the thread that's responsible for scheduling work to those streams. And we end up having a gap in the compute because I can't get it all scheduled fast enough. But what happens is the kernel scheduling is round robining between those different streams, and then a whole bunch of little stacking kernels at the end kind of constrict you, and you end up having all of the different streams end at the same time, and then I don't end up hiding my CPU section. So I think the key will be remove that synchronize and defer it till later. But overall, we found that SRME has widely varying compute requirements, and even within a single job, it's hard to take just a subset of the data set and say, oh yeah, optimize for this, and it'll be representative of the entire thing. And dynamic tasking is absolutely essential throughout every step of the journey. We were at least able to keep the highest level parts of the code common between CPU and GPU, and output sorting is essential for keeping the disk bottlenecks at bay. I'd like to thank at least Guillaume, the NVIDIA Guillaumes, Fatmir, and Nefeli for all their support, especially on the kernel development, my company Shearwater and coworkers, and then Geoscience Australia for the use of the Pluto dataset. So as mentioned before, if you want to know more about the actual plots, please reach out. I'd love to run this code on some other platforms or talk about it in more detail. Thanks.